Hello and welcome back to my CATIA V5 tutorial series. Today we'll be learning how to do kinematic simulations in CATIA. By the end of this video we will learn how to build this wonderful slider crank mechanism, I think it's called, and understand the different types of links between the parts and how to use them. First, we will start with my personal method of designing the mechanism and making sure that everything fits and everything works in the first place, and how to parametrically design everything so that it's very easy to change afterwards. If you're not interested in this part and all you want to do is find out how to link the different pieces together and make it work, you can go ahead and skip this part and just go to the second half of this video. But first, don't forget to leave a like, subscribe, and ring the notification bell. Now, there are scientific models to help calculate the links of the mechanism using reverse kinematics, but that is entirely out of the scope of this video. In this video, we'll learn how to do it quick and dirty using CATIA's integrated tools and make sure the mechanism works and we get the desired result. To get started, we need to create a new product, and inside we'll need to create one part for each link of the mechanism, including one for the fixed part of the mechanism. Even though if we don't add any geometry to it, it still requires a fixed part in order to operate. We will create also a part that is going to be our control part, the one that is like a master sketch that everything will be based on off of this. We will call it control part. Okay, now that we have our parts created inside our product, we can go ahead and rename the product to mechanism as well. We go into the control part. We can switch to generative shape design. I think this will be a lot easier. And we can create a sketch. Now, in this sketch, we should have some basic dimensions for our mechanism, for our links. So we begin like the drive link, which is going to go around the circle. Let's say around the point of origin. It's going to be something like this. You put some basic dimensions here for the radius. You have the second link, and then you have the final link, which is gonna be like a piston for us. You can define these like 220. You can define these this link here, the length, and you can see that this is kind of like a 2D sketch of exactly what we want. But I think we're going to want it a little bit longer because we don't want this to be sticking into this circle here. Not that it's not possible to have it, but we just don't want it. So we have this like 260, something like that. There you go. That looks perfect. Now, what we need to do is to create some output features from these. So this is like the drive link. This is the first link, and this is like this is going to be our piston. You see, you can find them here. You can rename them. Drive link. No, sorry. This is like the second link or whatever. And this is your piston, which is the end link. Now that you have your elements, you can go ahead and publish them. You go to Tools, Publication. In some environments you are required to publish these, some you are not. It doesn't really make a difference. And now you just need to copy them. So you copy the drive link to the drive link part, you create a new geometrical set, and you paste here with paste special, and as a result with link. And now this will be, you can see you have your little link symbol here. This will be linked to the line in this sketch actually, and it'll have this symbol on it. You do the same with the second link, or first link, or whatever you want to call it, and you copy it here. Now it's the end part that you copy here and link. Oh, if you just paste it here, it looks like it creates a geometrical set called external references, which is all by itself, which is good. And for the base, we are going to want maybe the drive link, the first and last. Normally we'll just need the last, but sorry, normally we just need the first, but in this case we're gonna need the piston, and you're gonna see why in a little bit. And paste it here as a result with link. So the reason why I said you need to publish them first is because in some environments you are not able to create links like this without the elements being published first. And now you just open each part one by one and start drawing stuff. This is our first link. So now that you have your input geometry, you can go ahead and create a sketch here. You create a circle here and a circle here. You project this onto your sketch. You make it a construction element. Now what you want to do is constrain this circle to not the origin. You press down arrow to select something else, and you pick the vertex from the drive link and pick coincidence. In this case, it doesn't make that much of a difference, but if you ever update your sketch and decide to have this point not in the origin, then you're gonna have a problem, because it won't update automatically. So here we put the diameter, let's say 60 sounds about right. 60 the same. We do this. Why is this a construction element? I don't want it to be. Then you do this. And then you I'm just gonna fast forward a little bit here, because I'm assuming you already know how to design some basic links. And while you do that, you can listen to this wonderful track I have selected. Okay, now that we have our mechanism, our links, for our mechanism, we can start actually building it. So in order to do that, we will have to use joints. These are the type of joints that you will be able to do in CATIA. Probably we will not have time to go through all of them, but I'll try to explain them a little bit. First thing first, we need, like I said, to have a fixed part of the mechanism, otherwise it will not work. So we select this anchor here, fixed part, and it requires us to make a new mechanism. New. Awesome. Mech. Okay. And we select this mechanism, which appears here. And we need to have the fixed, which is the base. In the base part, we will create our first link. So there are two types of revolution joints like this. We have the cylindrical joint and we have the revolute joint. Now, the difference between them is that the cylindrical joint will only require you to have a connection between one line from one of the parts and another line from the second part. So that means it will only constrain the rotation, the position of these two axes, meaning that then this part can fly all the way in this direction, wherever it wants to go. So it will not be constrained in this direction, but we want it to stay in this point here. So that's why we're going to use the revolute joint. Now, this joint will require you to put in two lines. One is this axis that we're going to spin around, and the other one is going to be an axis from the fixed part, which we don't have, and we actually need to go create it. So this part is basically empty at the moment, but we need to create something in it. So we'll open it in a new window because we don't have the required stuff in it already. We do have a plane, which we're going to use later, but what we need to do is have an axis in this direction, a line in X direction, like that. Wonderful. We can close this. We don't want to save any changes. Good. Then we go again with the revolute joint. We select this axis from this part, and then we make sure we have this selected here. And we have our lines. And secondly, we need to put our planes together. So we have one plane from the first part. The order is really important here. And the second plane, we need to choose the... Which one is it? This one, the YZ plane. Good, and this is the one that we'll actually use to put in the motion of our mechanism. So we have to check angle driven for this one because it's the one that is going to drive everything. Okay, revolute 1, that seems fine, and it tells us the mechanism can be simulated. But if we do that, we'll just rotate this around, and we want something more, don't we? We need another revolute joint here, but I will show you an example of how it'll work with a cylindrical joint. So cylindrical joint, it just needs two axes, this one and this one. Click OK. And you see this mechanism here, our awesome mech, has DOF, which stands for degrees of freedom equal to 2. And this is not good. It needs 0 in order to work. And why we have 2 degrees of freedom is that now it has two links, this one and this one. The first degree of freedom is the rotation around this. That needs to be somehow constrained because it'll not know what to do. It's not going to fall off. This is not a physical simulation where it simulates gravity, and that normally this would just fall into one position. It needs to be constrained in some way. So that's 1 degree, and the other degree of freedom is actually the contact between these two parts, because we have used a cylindrical joint and not a revolute joint. It does not know that this needs to be in contact with this. So we need to define that if we want to use a cylindrical joint. We could use just a revolute joint, and that'll just fix it. But I'm trying to show you all the commands and what they do, all the types of joints. So what we need to do is not a rigid joint. This will just fix them in place together, angle, position, and everything. What we need to do is this one, planar joint. So we select this plane, we select this plane, and the joint has already been defined between these two parts. We don't care because we want that. And you see the degrees of freedom has been reduced by 1, which is great. Now we need to connect these two together. How do we do that? With a revolute joint. We select one line from this, one line from that, one plane from this, and one plane from this one. We do not select angle driven because we don't want to drive this. And again, you see 2 degrees of freedom. Why? Why do we have 2 degrees of freedom? Well, because this can rotate, and the second degree, I'm not sure. Oh, yes, is because we do not define this angle of rotation. So it can rotate freely around this part. And now that we have more parts, then we have more degrees of freedom. So it's 1 extra degree of freedom. Now what we need to do is to somehow constrain this movement to block the movement of this piston in one direction. So to do that, it needs to have a joint to a fixed part, and luckily we already have our fixed base here. So how do we do that? We will put another planar joint, but this time we will need to get the plane from the end link, which is this one, XY plane, and constrain it to the XY plane of the base. And it gives us the message the mechanism can be simulated now with 0 degrees of freedom. So let's try it out and see how it works. See? Now that is what we want to do. We see this minus 360 plus 360. That is our command here when we have put our first revolute command, or revolute joint, and we checked this angle driven. We have our minimum and maximum limits, right? And there you go. That's how you build a mechanism in CATIA. What you can do now, we've done this kind of links to our parts with using our control part and our sketch here. The reason why we did this in the beginning is that now it becomes really easy to change. So this 260 millimeters, I don't want that. I want it 190. See? How does this look? That looks fine, right? Wanted to move this, but I don't know why it doesn't work. Yeah, see? This looks fine. Right, let's say that this is what I want now. And I want this to be, I don't know, 80 millimeters, like that. Do that, and then you just go into the parts one by one, and you need to synchronize. Right click, synchronize all. Right click, synchronize all. This one I don't think we need to do it, but we can do it anyway. Now you just need to update each one, or all of them at once. And as you can see, the mechanism automatically adjusted. to what we wanted. And now it's really easy to change this. It's super easy to do it. The other thing you can do is to compile a simulation. Well, not compile yet, but you can do a simulation. We want our awesome mech to simulate, and here you can add steps in the simulation. Let's say we start from minus 360, insert a step, then we go to plus 360, insert another step, then this is like the speed, how many steps it'll simulate in between. So this is like 1 second, I guess, and this is like 0.01 seconds. If you select this, this will basically mean it moves the slowest. And you can actually compile the simulation, and this will actually generate a replay. You can select the steps here, generate a replay. It will do this, and this will be 100% static. You can actually do this with it. You can do changes on the mechanism, and this will probably stay the same. This replay will stay the same. And you can also choose to create a video file from this. So you select here your codecs. This is like something you set up the video format you want, and select the file name, click OK, and it'll create a video file for this. And that's really useful to do. So what else can you do with the mechanism? You can create a sweep volume of this. You select your mechanism, products to sweep. So this is like the tolerance, filtering precision, 0.2 millimeters. You can simplify this. You actually might want to do this. Offset ratio, this is pretty much 0.1 should be fine, and preview it. And this will compute an offset volume of this. You usually want to have a small offset because of the graining. It's not going to be super precise. So that's why normally you want an offset. So see, this is the preview of the mechanism, and this is basically all the volume it occupies during its motion, and you can save this to your drive. One other thing I wanted to show you is the rigid connection between parts. So if I say wanted to put a screw in each joint here, you could insert a screw in your composition here. You then need to position this where you want it. Put it here, let's say. Put it here. And then you go back to DMU Kinematics and you create a rigid joint to, let's say, this part. And again, the mechanism can be simulated. And now this screw will basically be rigidly connected to our drive link. So one other thing you can do in this module, you can dress up your mechanism. So let's say you have designed these links and you want to, replace them somehow with like a static part that's not linked to this, or even a linked one. It doesn't really matter. But you still want to have these parts connected to your mechanism. You can, let's say, we're going to copy some parts from this product that I created offline before doing this. We're going to copy them here. And right, it doesn't let us do that because they have the same name, unfortunately. So we just create them as new parts. So we have this like mechanism superposed to this, and we want to dress up our mechanism. We create a new Dressup. We select our mechanism, and then here we have the parts for which we created Dressup. This is part 1.2. Fortunately, this is the instance name and not the part name. This is the drive link 1.2, and we select another part for it to dress it up. And it's this one, copy of drive link 1. Copy of drive link 1. Good. And we link that to that. The next one is 1.5. 1.5 is the fixed part. We don't want to dress this up. 1.3, first link, and we need to replace it with this one. Copy of second link. Part 2.1. 2.1. This would be a lot easier if these actually had names to them. 1.4, end link. This is our piston basically, and we want it to be this one, end link 3.1. Good. So now this part, the 4.1, which is our end link, is going to be connected to the 3.1, which is our end link from this one. You could do anything else. You want to add some parts to design it. It doesn't have to be the same or similar. It's basically just connecting two parts together. And now we have our Dressup for this mechanism. And if we simulate this, you can see that the parts from my original mechanism will follow the rotation. You can go ahead and hide the previous one and hide the screw as well. Now, because this mechanism, these links are different, they will not match. But this way, you can have different files, different files, and dress up your mechanism however you want, without changing the original files. So this can stay like your control geometry, your initial input, and after that, these parts can be designed in isolation, and you can just replace them here. That's something else you can do. So that's about it for today. Thank you very much for watching. If you enjoyed this video, leave a like, subscribe to my channel, and ring the notification bell. And see you next time.